attempting to lift a piece of machinery using, a machinery of weight W equals 1 kilonewton. So as I always say, if you get numbers that have powers in them, it's always worth just highlighting it and probably correcting the power when you get to it. So 1 times 10 to the 3 newtons using a uniform iron bar of weight 0.2 kilonewtons. So we're probably all okay to convert this to 200, but just to avoid making the mistake and not converting it to 200, let's write it in with the power of 10. So numbers written like this in maths are not acceptable because this number should be bigger than 1, but in physics this is absolutely fine. He uses a pivot placed as shown. Calculate the magnitude of the force which he must apply downwards if he is to lift the machinery. So we're going to take some moments around position P, pivot, and in terms of clockwise moments, we've just got 1. It is the force of 1 times 10 to the 3, and it is acting at a distance of 0.2 meters. I have 2 anti-clockwise moments, one provided by the weight of the bar, that's 0.2 times 10 to the 3 at a distance of 0.2 meters, and the one provided by the man pushing downwards. It's also minus size F, distance 0.60 meters. And for him to be able to just lift it, so that the moments are balanced, we're going to say that's equal to 0. He'll obviously need a slightly bigger force than that to accelerate it at the start, but we're going to say the acceleration is very close to 0, so the force is exactly equal to it. So just some rearranging to do here. We're going to move this term to the other side and then divide both sides by 0.6. So that should give us F. So we've got these two together are 0.2 times 10 to the 3. So we could just write that as 200, can we? As 200 Newton meters in the clockwise direction. Take away the bit that we've got in the anti-clockwise direction. This is 200 times 0.2. So I think that should be 40 when we work it out. Obviously, if you just type these into your calculator, that's absolutely fine. So 200 minus 40 is 160 divided by 0.6. Gives a value of 270. We're good on significant figures in this question, so it has to be to 2. So 270 newtons to 2 significant figures. Then the reaction force provided by the pivot. Again, as always, 2 options. One option is to take moments. One option is to look at the total upwards force and downwards force. But the thing we're practicing is moments, so why not do it that way? I'm going to call this man M, and I'm going to take moments around the man. There's loads of different places we could take moments because we know all the forces. So taking moments around the man, we've got 1 clockwise force here. So this has a size of 2 times 10 to the 3 newtons and is acting, have to be a bit careful here with distances, a distance of 0.4 meters. We've got another clockwise moment over here. This is the weight of the machine, which is 1 times 10 to the 3 newtons, acting from the man a distance of 0.8 newtons. So 0.8 meters. That's the unit of distance. Then we have one anti-clockwise moment. It's the one that's caused by the force coming from the pivot. I'm going to call that P, and it is a distance of 0.6 meters from the pivot, and it's acting in the opposite direction. Sorry, from the man, not from the pivot, from the man. These have to be equal to 0. So again, we can work out our value of P. So I'm going to move this term to the other side to make it positive. Then I can divide both sides by 0.6. So P should be equal to these two terms divided by 0.6. So we've got 0.2, so 200 times 0.4 So 2 4s are 8. So this must be 80. Yep, I think that's right. And 1,000 times 0.8, well, that's obviously 800. So 880 divided by 0.6 gives a value of 1,500 to two significant figures, 1,500 newtons.